introduce yourself.
Yep. My name is Benjamin Perseghetti. This is Landon Haugh. And we basically are going to be presenting some of our work with hardware and loop simulation, specifically focused on ROS2 and PX4. And we're going to first go over a little bit of some of the hardware associated with our hardware in the loop. And for that, I'm going to have Landon present some of the hardware.
All right, so I guess first I'll go over the buggy kit. So this buggy kit here is a platform that we'll be using for our upcoming Hover Games 3. So if you've heard of Hover Games before, it's a drone coding competition run by NXP and Hackster.io. In the past, we've seen that there has been some people, maybe in Europe and other parts of the world, that don't have access to flight in their countries because of regulations. So we created this buggy kit as sort of a sidestep to that. So we've been building upon this platform with our mobile robotics solutions. The first of which is the NavQ Plus. So last year in Hover Games 2, we used the NavQ, which was based on the IMX-8M Mini. This year we're using the NavQ Plus. This is using the IMX-8M Plus SoC. So it's got 4 Cortex A53 cores, 4 gigs of RAM, which is pretty much the same as last time on just the normal NavQ, but we have some upgrades this time. It's got a 1080p 60 H.265 and H.264 encoder and a dual camera ISP. The big selling point here is the neural processing unit. So this is a 2.3 TOPS NPU. You'll see in the demo we're running a TF Lite node on it that is able to run inference on a COCO data set at about 13 milliseconds per frame. And this is all within about a 5-watt envelope. We also have dual CAN-FD on board. So you'll see that we're communicating with another one of our boards using CAN-FD to do this demo. And dual MIPI CSI, so you can hook up dual cameras to this and run stereo vision. It also has 2.4 and 5 gigahertz Wi-Fi and Bluetooth 5.0, as well as micro HDMI and dual USB-C as for upgrades over the normal NavQ. So on top of that, the software stack that runs on this board is Ubuntu 20.04, with 22.04 coming soon. It's running ROS2 Galactic, with Humble coming soon, of course. And then we have some vendor-specific libraries running in GStreamer and OpenCV, as well as TensorFlow to do the inference and all the software that's happening on this demo. The next board on this kit is the UCAN S32K146. So this is a CAN node with dual CAN-FD transceivers as well. It uses our S32K146 automotive processor. So you'll typically see this processor in like ECUs or body control modules, but we're using it here in a mobile robotics application. This runs PX4, and it's actually sort of the hub for controlling the motors, servos, and lights on our car. So the way that it's doing that is it's communicating UORB back and forth with the NavQ Plus over SIFL. So essentially we have built up a ROS2 to UORB bridge using SIFL as the transport. And you can connect I2C, SPI sensors, UART sensors. It's even got dual PWM interfaces on it. So think of this board as a CAN hub for all of your sensors and devices that you would typically connect up to, like an I2C or SPI port on your flight controller. And as I said, this is controlling the LEDs and PWM outputs on our car. And I just went over that. So Benjamin's going to talk about the simulation environment.
Yeah. So for our simulation environment, we are using Ignition. I don't know if any of you are familiar with Gazebo in the past. Ignition, which has actually now been renamed Gazebo, has been a long-time simulation environment associated with ROS2 and OSRF. We have it both running in Fortress as well as Edifice. Currently on our demo laptop, we are doing it in Edifice Ignition. We have models, multiple models that we've actually already created that are already fully open source that people can utilize. specifically for NXP-based competitions, one including the Buggy 3, as you see here in that image, going around a race course that we provide as well. We also have the Hover Games drone. That is a very specifically laid out drone that matches the Hover Games drone kit drone, and also a new development platform called El Mandadero, which is more targeted towards a segment of doing deliveries and is a lot larger of a vehicle, but is a general platform that allows you to do a lot more than what you could do, for instance, with this smaller size buggy that's used in the NXP Cup and Hover Games. So everything associated with this is controlled through ROS2. As Landon had previously touched over with SIFL, we are more or less sending SIFL-specific messages over ROS2 that gets listened to in a node and then gets republished over a ROS2 socket can node, that SIFL frame. That SIFL frame then ends up getting more or less ingested on the UCAN board or the CAN node board in PX4, and then it takes that SIFL frame and drops it into a UORB message, which then obviously runs inside of your typical driver framework or any other kind of thing you have downstream from that. And so the main thing we also want to show with this as part of this integrated simulation setup is sometimes when you're trying to characterize a new sensor or you're trying to do something that you might not have, parts might not be available for a OAK-D sensor that you might want to be trying out, or for a real sense, you can't get access to it, you're changing resolutions, you're not sure how it's going to affect your NPU performance or your inference engine. What you can do instead is simulate that, those sensors, and then feed it through. So in this case, we have our simulation computer here that is running only simply ignition, so the actual visual rendering to basically feed across over Ethernet directly into this NavQ Plus connected via Ethernet. And what that allows us to do is more or less feed it whatever kind of unique sensor data we want, and mix that with also real sensors. So this cup does not come part of the kit, but we put that on there so you're not going to have to see it light up a whole bunch when it sees people. But we have multiple inference engines. We have coming out of our TF Lite model that runs on this NPU, a DDS message also that you can then ingest anywhere on the network for inference. That is fully customizable to whatever TF Lite model you're running on the NPU. And so, for instance, we have two TF Lite messages coming out. We have one associated with our real camera, and we have one associated with our simulation camera. And what we're going to show basically is it recognizing stuff in frame, specifically people, and then controlling the behavior of the input from our actual controller in the simulation, and then also providing LED feedback, for instance. So if you're, in other words, somebody who's not looking at, for instance, an image frame, and if this was running around inside of a warehouse, or if this was doing something else, you would want to be able to see, okay, there's somebody in the way, I don't want to be able to just drive over them. So for instance, this is going to show how in PX4 it's going to lock out the ability for basically the PWMs to be fed once it recognizes inference engine on the real camera that there's a person. As you can see also right here, as Landon is showing, here's this vehicle in simulation. We also, for those of you familiar with Gazebo, have Rescue Randy in the background that we will drive over and see. And as you can also see, I believe this right now should be showing a frowning face because Landon is standing right now in front of it with a high enough inference to basically have it say, nope, you're not allowed to go. So now he's allowed to drive it around, and he'll drive it around until he, for instance, sees Rescue Randy.
Well, I'm going to show him.
Okay. So before he sees Rescue Randy, it sees him. Immediately cuts the motors off. And this is just an example to show you what you can do with this kind of integrated setup, because once again, everything that's happening on here is more or less a ROS2 DDS to CAN SIFL to UORB. And so this is a very convenient way that you can add multiple PX4 nodes directly on There you go. See the person screaming, sees person. Multiple ways that you can add, obviously with CAN networks, multiple CAN nodes that can be ingesting more or less these DDS topics in a way that is simply much more difficult to do through other means, such as Ethernet, et cetera, because you can just daisy chain these CAN nodes more or less, and it's very easy to manage to do that. So you'll see it does the little displays. For instance, it will be flashing like a little hazard sign, and a little rescue Randy sign, and a stop sign, and more or less the goal behind this is showing you that it's very easy to transition, and all this code is upstream and open source, to be able to more or less show directly what you can do with using an NPU inference engine and being able to then directly feed that into PX4 over SIFL and a UORB topic inside of PX4. So it's a novel way that you don't now have to worry about compiling with IDLs through XRC DDS necessarily, or through micro RTPS that you would have to normally do otherwise to be publishing directly to a UORB. You can connect multiple CAN nodes and not have to worry about really any extra configuration, because it's simply going to ingest the message you set. And you can set just like with anything. And if you're not, does anybody know what SIFL is? How about we raise hands if you know what SIFL is?
Or UAV CAN.
Or UAV CAN. You've heard of UAV CAN? Okay. All right. So because this is confusing, UAV CAN V1 was recently renamed to SIFL, or Open SIFL. So when we're saying Open SIFL, we really mean UAV CAN V1. And that's what's running on these CAN nodes. And that is more or less what we are highlighting as part of the simulation framework, because this, at the end of the day, can control whatever really kind of sensor or data you want over CAN now with PX4. And that's something that was not arbitrarily easy to do previously if you wanted to keep adding on different endpoints on a network. But because it is over CAN, and you can add multiple onto a bus and communicate with them, it's a lot easier. Do you have a question?
Yes, this is CAN bus.
Yep. So UAV CAN runs over a CAN bus. So SIFL is UAV CAN V1. It runs over a CAN bus. Specifically in our case, we're running CAN FD. So we have larger data frames to send, and that's how we're able to send all this data. Actually, do you want to do a CAN dump on it?
So essentially, UAV CAN is a stack of layers. You've got your presentation layer, you've got your transport layer, and essentially we're just using the transport layer of UAV CAN or SIFL. So what we're doing is we're taking a UORB message format in ROS2, and we're doing all, just the bit shifting and stuff to package up these bytes, and then send that using a SIFL transport. So we're setting a node ID, a port ID, and we're packaging out the payload. And then there's a SIFL driver that runs on the UCAN board itself in PX4 that will then take in CAN frames and then convert those CAN frames to an actual UORB message and publish it to UORB. So essentially, we're just taking data from ROS2, packaging it up into a SIFL transport, and then sending it to be published to UORB in PX4.
And that extends even further, though, for instance, because if you have other endpoint sensors, you can have it go the opposite way, where you can now have a SIFL message be sent back across and be read and then fed back into DDS ROS2. So it's basically a two-way bridge using CAN and connecting back to ROS2 and DDS that doesn't really require any pre-knowledge of having to worry about any IDL structure matching. So you basically get to choose what you want to have your end UORB message, and then more or less send that across that SIFL message. Any questions offhand? I know we sort of blew through that, and it's probably confusing because I realized when I started saying SIFL, since of the recent name change, people are probably like, what on earth? So are there any questions in regard at least to the CAN aspect or SIFL aspect still? Got a question?
So very broad, and I apologize, I'm kind of new to the field, but how many devices are payloads, so external to your FMU are supporting CAN?
So right now we just have one CAN node running all of this, because the CAN node is able to basically have so many outputs that you really have a lot of levity and ability to choose what you want to do even with just one CAN node. But we also have used multiple CAN nodes, as on this nav queue there's 2 CAN buses, and each CAN node has 2 CAN buses. So what you can do is you can take in a CAN message and send it right back out daisy chained on it, or you can send 2 separate basically CAN buses depending upon the priority of message you want. So is anybody really sort of familiar with CAN actually, first off? A little bit?
So I'm looking for the ECU right now.
Looking for the ECU? So, sure.
So
Yeah.
CAN is essentially just a serial protocol that's very robust because it's a differentiating signal. So with CAN-FD is sort of the upgraded version of CAN. You get a lot more bandwidth. You can get up to 4 megabits per second. Now with normal CAN, you get a maximum of 1 megabit per second. You can connect as many devices as you want onto the bus, and all of them can talk to each other simultaneously. The only issue is once you start saturating that bus is when you run into issues. So you're sort of limited by the amount of data that you can pass along the bus, but CAN is limited to these 64-byte CAN frames. So really you can only send so much data in a single CAN frame. So when you're using CAN, you're not really sending like huge amounts of data. It's really just the essential stuff that you need, but it's an incredibly robust protocol. That's why it's used in cars, rockets, planes,
What is the
whatever.
roll time constant?
Is that from the other?
It's like, I didn't say that. I don't know.
Yes, so that's the whole point of using CAN in this space, is because NXP ourselves is very heavily focused in automotive. And we have these automotive microcontrollers and automotive application processors that use CAN a lot in vehicles. So we're just showing the technology that you can use with automotive processors in this mobile robotics space. And so we're taking all this and putting it into PS4.
And also showing how that you can also test a lot of this, because, you know, this thing isn't as scary to drive around in your yard, but if you're doing a larger vehicle, definitely could be a lot more scary. So being able to then take all of this and test directly from simulation, and also have mixed sensor usage, like we have both a real sensor, right, and then also you know, our mixed sensor, really allows you to do a whole slew of testing over CAN that is very difficult to do otherwise in the real world. So that's sort of what we're, you know, that's the aspect that we're trying to highlight here, is that you can now have more or less simulation directly hooked up to any sort of PX4 sensor and device controller through these CAN nodes. As long as you more or less have something that has socket CAN attached to it that's Linux based. In this case, that's our NavQ Plus that runs the NPU on it. But you could be doing any kind of inference engine, any kind of endpoint. Obviously, we chose this one because that's the hardware that comes with this particular kit, and we're trying to highlight that because it's a very complete kit in that regard. So that's more or less the main aspect, though, going back to CAN again, is that you get that CDMA, collision detection, that you don't get really with other forms of communication. So it really handles priority and messages on buses a lot better than other ones, and yet you get reliability because it's very simple. If you were to look at, for instance, at UAV CAN V1 or OpenCyphal and look at how they basically manage sending messages as well at that transport layer, it does actually a very effective job of making sure that you get messages effectively transmitted back and forth, including the heartbeat on it.
I had my thing turned off.
Okay.
Were there any other questions that anybody had, or any other things? Yep, in the back.
So, OpenCyphal is looking at time-sensitive networking Ethernet as the future medium. Correct me if I'm wrong. How difficult or easy would it be to port this code to different medium like Ethernet?
So pretty straightforward, easy, at least for doing Ethernet, because that's sort of the default of what already DDS is set up to run over, you know, UDP. So it shouldn't be that difficult, and I believe that there's actually some work already done with TSN associated with DDS specifically with the IMX8MP, which is what's the NavQ Plus. And I believe that's already actually been pushed up in open source. I could find the references to that and hand it to you later if you have interest in that. See more details on that. I don't have it on hand with me right now. But there has been already work done with that. So I would imagine that porting that over to include that would not be that difficult. But of course, you don't know until you actually try, right? Everything's easy on paper until you actually do it. Any other questions about networking or simulation or anything else that you guys desire to inquire about?
I will say that we have a booth that we'll be showing this demo at. So if you're curious and want to have an actual conversation rather than just asking a question here, we will be there both days, all day pretty much. So yeah, you can come pick our brains about this stuff and get more details about it if you'd like to.
And if you want to see more details about how the ROS messages work and exchange, we'll go into that. We pretty much don't want to show everybody every single last DDS message that's going back and forth on this thing, because I don't think that would be a wise use of anybody's time. But that will be at the booth as well if you want to look at the different outputs and messages coming off of this. And once again, I will highlight, if you do stuff with inference and using TF models, this does already send from this NavQ out on a DDS topic in ROS2 the output of any TF Lite model that you want to run with the delegates that get loaded for that model. And you can choose to send that out onto any network. So you can use also this NavQ as basically a sink if you want to on a network to do inference and just read whatever image you want to feed to it, and multiple images in this case in that same inference engine that we're running, and have an output. And it is designed to be modular. So if you have a TF Lite output that, for instance, does not have the indices match up with the same B box and label and score, you can actually set those indices when you run it to allow you to have them correctly align and be packaged correctly into the message for that inference engine. So I think we'll probably wrap up for the most part, unless if there's any further questions or if anybody else wants to see other things. Of course, once again, with the simulation, the main key highlight behind it, once again, is that we are trying to show the power of basically driving only off of this computer, the simulation itself, and everything else run actual hardware in the loop. So all this provides is the physics, because obviously you don't want this guy driving around, in the demo, it'd be a little scary. And this provides the physics and the visualization of the output of what this would actually be doing, and that everything else is running as if it were to be unplugged from the computer and run real world. So, well, if there's no further questions, we'll probably wrap it up. Thank you guys for your time. I appreciate it, and welcome to always swing by the booth if you have any further questions or if you want to play with anything else. And we also have some other stuff at the booth, including our new V5X, I believe, sitting there, as well as a new automotive part using the S32K3 that will be presented by our colleague Peter Vanderperk tomorrow as well, associated with what can be done with that automotive part. All right. Thank you guys very much. Appreciate it.